In this lesson, I'd like to shift gears a bit and talk about solving a new type of system. This time, we're going to talk about systems of linear inequalities. So instead of studying equations like y equals 4x plus 2, we'll be looking at inequalities like y is less than 4x plus 2, or y is greater than or equal to 4x plus 2. Before we begin even talking about these kinds of systems, there are a few questions we need to answer. First of all, what does a solution of an inequality look like? Well, let's go back to the inequality y is less than 4x plus 2. Notice that one solution of this inequality is the point 1, 3, because if we plug in x equals 1 and y equals 3 into that inequality, we're going to have 3 is less than 4 times 1 plus 2, or 3 is less than 6, and that's a true statement. So that would be one solution. But the next question to ask is, what do all of the solutions look like? Or what does the set of all solutions look like? How can we see that? How can we visualize that? Well, the answer is pretty simple. We start by graphing the straight line y equals 4x plus 2. This line is going to serve as a boundary or as a wall, cutting the xy plane into two pieces or two regions. One region which is above and to the left of the line, and the other which is below and to the right of the line. It turns out that all of the solutions of the inequality will be in one of these two regions, or halves of the xy plane, if I may call them that. So the real question is, which half is it? Well, remember that we already showed that 1, 3 is one of the solutions. So where is the point 1, 3 compared to the line that we drew? Well, it's in the region of the plane that is to the right and below the line. And that tells us everything we need to know. The set of solutions to the inequality y is less than 4x plus 2 is the whole part of the xy plane that is to the right of and below the line y equals 4x plus 2. So when we graph this inequality, we actually shade in that whole region, and we're done. Now, I need to make one subtle point that's very important about the example we just did, and then we'll move forward. When the inequality is a strict inequality, in other words, when the inequality symbol we're dealing with is strictly less than or strictly greater than, we're actually going to draw the boundary line with dashes to remind us that none of the points that live on the line are actually in the set of solutions. But when the inequality isn't strict, so when we're working with less than or equal to or greater than or equal to, then we're going to draw the boundary line as a solid line. And that's going to remind us that the points on that line really are in the set of solutions. Okay, there's one more issue to think about before we jump into some examples of systems of linear inequalities. What will the solution sets look like if you're looking at the system of linear inequalities? Remember, when we're solving systems of linear equations, we're looking for intersection points, and we'd like to find a unique solution in that process, assuming the system is independent. Well, when we're looking for solutions of systems of linear inequalities, we're still looking for intersections. But now we're often going to be finding the intersection of two regions of the plane, two pieces of the plane, not just the intersection of two straight lines. So the solution sets are going to be big, and the easiest way to see them or to find them is to actually visualize them on the xy plane. So we're going to go back to the method of graphing that we talked about a few lessons ago to actually find these sets of solutions. Okay, now that we've made these sort of opening comments, let's start looking at some very specific examples of solving systems of linear inequalities. The comments I made earlier were really just about one linear inequality. Now I want to consider 2 linear inequalities at a time, and I want to solve those kinds of systems. So here's an example. Solve this system of linear inequalities. Y is less than or equal to 4, and y also needs to be less than or equal to 2x plus 1. So let me just make a quick comment. In order to solve this system, I want to find all of the points in the xy plane. Those points are going to be x comma y, such that the y's are less than or equal to 4, and the y value has to be less than or equal to 2x plus 1. I need all the points that solve both of those inequalities at the same time. All right, how do we start? Well, we start by drawing, if you will, these boundary lines. So I look at my first inequality, and I see that the boundary line for that is going to be the line y equals 4. Remember that that's just a horizontal line which crosses the y-axis at 4. Okay? I then look back at the inequalities, and I remember that I'm looking at y is less than or equal to 4, and those are going to be the points below the line y equals 4. For example, the point 3 comma 1 is a solution of the inequality y is less than or equal to 4 because 1 is less than or equal to 4. So I know that whatever I shade in needs to include the point 3 comma 1. So I shade in this region, which is below the line y equals 4. Notice also that that inequality, y is less than or equal to 4, is not the same as y is strictly less than 4. What does that mean? Since I'm dealing with y is less than or equal to 4, my boundary line is going to be drawn as a solid line rather than a dashed line. Okay? So, I've actually done everything I need to do now with y is less than or equal to 4. I've drawn a solid horizontal line through the y-intercept at 4, and I've shaded all the points below it because all of those points represent the places where y is less than or equal to 4. Now, on this same set of axes, with all this shading already done, I now want to look at the second inequality. It was y is less than or equal to 2x plus 1. The boundary line for that inequality is going to be y equals 2x plus 1. And that line is pretty easy to draw. If you think back to some of our earlier lessons, it's the straight line with y-intercept 1 and slope 2. So we ought to be able to draw that pretty well, and that goes pretty quickly. Now, next question, and you should always ask it at this point, is it a solid line or is it a dashed line? It's very important. Well, this inequality is a less than or equal to inequality. Remember, we're doing y is less than or equal to 2x plus 1. That's not a strict inequality because it includes the equals. And therefore, when I draw this boundary line, I'm also going to draw it as a solid line. So I have two different boundary lines, and in this problem, they're both solid, not dashed, because both of the inequalities included the equal sign. Now, I need to shade in the points which satisfy y is less than or equal to 2x plus 1. I've basically got two choices of shading. I can either choose the points which are below and to the right of the line, and in order to do that, I could check, for example, the origin at 0, 0. If I plug in x equals 0 and y equals 0 into the inequality, then I would have 0 is less than or equal to 0 plus 1, or 0 is less than or equal to 1. Is 0 less than or equal to 1? Yes, it is. So we want to shade in the region that includes the origin 0, 0. And that's the region that is below and to the right of this line. Now, your paper might be getting a little colorful right now. There might be a lot of shading going on, but that's okay. Let's now finish the problem by interpreting what we've done. Once you've shaded in these two separate parts of the XY plane, there was a part below the horizontal line, and now there's another part below and to the right of that other line, you actually see four regions of the plane. There's going to be a region that didn't get any shading at all. There are two regions that have just one shade, if you will, and there's one region which was actually shaded two different times, once for the first inequality and once for the second inequality. That region that has the two different shades is actually the intersection of the two sets of solutions for the individual inequalities. And it's that region, the set of intersection points, which are going to satisfy both of the inequalities at the same time. Guess what? That shaded, if you will, double shaded region, the set of intersection points, is the final answer. So that part of the plane turns out to be the solution set for the system of inequalities. Now, we could check our answer, and we really should check our answer, but how do you do that? Because now we have all of these points in the xy plane which are actually in the set of solutions. Well, let me make this suggestion. Just pick one or 2 points that are in this region that you think is your set of solutions, and choose the x and y values of that point, or a couple points, and plug those in to both of the inequalities in the original system. If you do that pretty quickly with 1 point, it'll at least be a decent check that you're probably on the right track with your solution set. So let's do that here. One of the points in our region that appears to be the solution is 2, 0, which is right on the x-axis. Let's check to make sure that that point really is a solution of the two inequalities. All right, so first we had y is less than or equal to 4. The y-coordinate of the point 2, 0 is the 0. Is 0 less than or equal to 4? Yes, it is. So that point really is in the solution set for that inequality. Now let's try the same point in the other inequality. Y is less than or equal to 2x plus 1. If you let y be 0 and the x value be 2, because I'm looking at the point 2, 0, then I have 0 is less than or equal to 2 times 2 plus 1, or 4 plus 1, which is the same as 5. And you have to ask yourself, is 0 less than or equal to 5? The answer is yes. So we know that that point actually satisfied both of the original equations, or inequalities, I'm sorry, these aren't equations. It satisfied both of the original inequalities. And because of that, we know that that 1 point is in the solution set, and we have confidence then that the region of the xy plane, which was the intersection of the two regions, really is the set of solutions for that system. Okay, I'd like to move to another example, but this time I want you to try to graph it yourself first. Now you need to be careful of a couple things. Remember, first, you need to ask yourself about the direction of the inequality. Are you working with a greater than or a less than? That's very important. And secondly, also keep in mind that you have to worry about whether your boundary lines are solid lines or dashed lines. Remember, if the inequalities are strictly greater than or strictly less than, then the boundary lines need to be drawn with dashes. Okay, here's the system of inequalities I want us to now consider. Solve the following system. Y is greater than x minus 3, and 2x plus y is less than 4. Now, the first thing you need to notice, as I mentioned a few minutes ago, is that both inequalities are strict here. One is a strict greater than, and the other is less than. And that means that both of the boundary lines that you draw are going to be dashed. Okay, so that's the first thing we need to notice. By the way, in some other examples, you might have one of the inequalities which is strict and another inequality which is not strict. You might have, say, less than for one of them and greater than or equal to for the other. That means that one of the boundary lines would be dashed and the other boundary line would be solid. That's perfectly fine to do that. In this case, both of my boundary lines in this example are dashed because both inequalities are strict. All right, now let's start by drawing the first boundary line, and in this case, that's going to be y equals x minus 3. Now the beauty here is that that's already in slope-intercept form, slope of 1 and y-intercept of negative 3. So that's not hard to draw. That's great. Remember to draw it dashed because the inequality was strict. Now, in this case, I want to shade in the points that satisfy y is bigger than x minus 3. So here's a question. Which part of the plane do you think this represents? It's either the part that's sort of above the line and to the left, or the part that's below the line and to the right. So if you're not sure which part it is, let me give you a hint. As soon as you can find one point that's in the right region, then you know that that's the region you have to shade in. That's all you have to do. So I'm going to pick a point, and I'm going to try to do it sort of intelligently to minimize my work. Okay? You might think of it as mathematical laziness. I don't want to think of it that way. I like to think of it as mathematical intelligence. I'm going to pick a point which I can plug into the inequality and quickly check to see if things are true. And I think the best point for that is the origin, where x is 0 and y is 0. So here's what I'm asking now. Is the origin in the solution set of the inequality y is greater than x minus 3? Plug in 0 for x, plug in 0 for y. Let's see what you get. The left-hand side, y, is just 0. The right-hand side becomes 0 minus 3, which is negative 3. So the inequality says 0 is greater than negative 3. Now, you got to pause and ask yourself, is 0 greater than negative 3? Well, the answer is yes. And if that's a bit confusing, by the way, draw a quick number line, plot 0 and plot negative 3, and ask yourself if 0 is to the right of negative 3. And it is. So the answer to whether 0 is greater than negative 3 is yes. And that means that the origin is in the solution set. So I need to shade the part of the plane which is above and to the left of the line. Because do you see that the origin is above and to the left of the line? Good. Now you've done basically half the problem. You started with the first inequality, you drew in its boundary line, in this case, dashed, and then you shaded the part that's above and to the left, because that's the part that satisfies that inequality. Now, let's move to the second inequality, which is 2x plus y is less than 4. Well, I got to start the same way, draw in the boundary line, which is the line satisfying 2x plus y equals 4. That might not be the easiest thing to draw until I rewrite it in slope-intercept form. But that's not too hard. Just subtract 2x from both sides, and you'll have y equals negative 2x plus 4. And that's in slope-intercept form. Slope of negative 2, y-intercept of 4. And once you know that, you can plot that line pretty quickly, and you'll have your second boundary line. Now, remember, that line has to be dashed. I'm sorry to keep harping on it, but it's an important, albeit subtle, fact that you have to keep in mind. Now, you've drawn that second boundary line. You still need to shade in the region of the plane that's being cut through by that line. In other words, you've drawn the second line at y equals negative 2x plus 4. It has now sliced the plane into two pieces. Which of the two pieces corresponds to the solutions of y is less than negative 2x plus 4? Well, you have the points which are below and to the left of the line, and you have the points which are above and to the right of the line. Which ones do you choose? Well, you pick the ones which are below and to the left of the line. And that's because the y is less than negative 2x plus 4. Remember, if you can tell which region to shade, or if you're having trouble with it, I should say, just pick a point on one side of the line. If that point makes the inequality true, then you shade that side. If that point doesn't make the inequality true, then you shade the other side of the plane. It's actually that simple. So now we shade in this region as well. And what you see, just like in the previous example, is this. Your XY plane now has 4 different pieces. One that has no shading at all, 2 that have just one color of shading, if you want to think of it that way, and then there's a 4th piece that's the overlap where the 2 different colors have now combined. It's that overlapped region which represents the intersection of the 2 individual solution sets. And that intersection is exactly the set of solutions of the system of inequalities that we started with. Every point in that intersection region satisfies the original system of inequalities, and that's the final answer. Okay, let's look at another example now, just to continue practicing, if you will, with these systems of linear equalities and how to solve them. Here's the system. Let's take y is greater than negative x and 3x minus y is greater than or equal to 2. Now, let me start by suggesting that we write both of these inequalities in such a way that the equations for their boundary lines are easy to see. You're going to have to draw the boundary lines eventually. So let's just rewrite these things so that they give us a better hint as to what the boundary lines look like. The first inequality is actually already in such a form because the boundary line for it is just going to be y equals negative x. That's nice. It's a very straightforward line to draw. The other inequality isn't yet that clean looking. So let's just kind of manipulate it a bit to make it look like the boundary line is much easier to see. So that equation was 3x minus y is greater than or equal to 2. I referred to that as an equation. It's not an equation, by the way, it's an inequality. 3x minus y is greater than or equal to 2. If I add, or in this case subtract 3x from both sides, I get negative y is greater than or equal to negative 3x plus 2. Now let me just remind you of something. When you add a negative 3x like that to both sides of an inequality, or if you want to think of it as subtracting 3x, the symbol, the inequality symbol does not change. So I'm now at negative y is greater than or equal to negative 3x plus 2. In order to clean that up just a bit more, I want to multiply by negative 1 or divide by negative 1 so that I just have y on one side. And when I have that, I'll have y is less than or equal to 3x minus 2. When you multiply or divide by a negative number like negative 1, that's when the inequality symbol must switch. So my inequality now is really a less than or equal to, it's y is less than or equal to 3x minus 2. So I have that inequality, and the other one just comes along, y is greater than negative x. Perfect. Now, I've accomplished something. I can now sort of see the boundary line equations much easier. I've got y equals negative x, and I have y equals 3x minus 2 as the boundary lines. So, what are the steps now? You need to draw those boundary lines. We have to shade in the correct regions, that's important, and then we find our solution set by looking for the intersection of the two shaded regions. Let me suggest that you try that yourself now. Let me remind you what you're doing. You want to solve this system. Y is greater than negative x, and y is less than or equal to 3x minus 2. Try it yourself. See how you do. Okay, now let's see. Let's walk through the steps, and let's make sure that we got the same answers. That's always fun to do. So the first boundary line is y equals negative x. That's pretty easy to graph. That has the origin as its y-intercept, because it's the same as y equals negative x plus 0, and it has a slope of negative 1. So it's going to slice right through the origin with a slope of negative 1. Okay, that's perfect. Remember that this first inequality is a strict inequality, so that boundary line needs to be a dashed line. Now, I want to pick the right region where y is strictly bigger than negative x. Now, unfortunately, the origin, which is my favorite one to pick, is right on the boundary. So I can't choose that. So I need to pick another point somewhere in the plane and check to see if that point is in the solution set for that inequality. Let's pick something like 4, 2. Okay? If you let x be 4 and y be 2, and you plug those into the inequality, you're going to have 2 is greater than negative 4. That's a true statement. So I want to shade in the region which includes the point 4, 2. And that's going to be the region which is above and to the right of the line that I drew. Okay? So that's so far so good. We've got basically half of the problem now done. I've shaded in the part of the plane that's going to satisfy the first inequality. Now, let's try doing the same with the second inequality. I need to start by drawing the boundary line for that inequality, and that's going to be y equals 3x minus 2. And that's going to be a solid line because the inequality that it corresponds to is y is less than or equal to 3x minus 2. And drawing y equals 3x minus 2 isn't too hard. I've got a y-intercept at negative 2, and I have a slope at plus 3. Okay, now I've drawn my line, and I've drawn it as a solid line in this case, and now I need to see which region I should shade. And now my good friend, the origin, is something I can plug in, and I can check to see if the origin is in the solution set for this inequality. So let's try it. I'm going to plug in y equals 0, and I'm going to plug in x equals 0. And when I do that, I'll have 0 is less than or equal to 3 times 0 minus 2. And that's the same as 0 is less than or equal to 0 minus 2, or 0 is less than or equal to negative 2. Now, is that true or false? That's false. And that means that for this inequality, the origin is not in the region I want to shade. And that means I want to shade the region on the other side of that line and avoid the origin in that case. And at that point, I'm back to the same kind of problem I had before. Namely, I've taken my xy plane and I've drawn two boundary lines. I've shaded in the appropriate pieces, and the xy plane is now colored in 4 different ways. There's a part of it that has no shading. There's 2 parts that have 1 color of shading, and there's this 4th part that has the intersection, if you will, the 2 different shadings overlapping one another. And it's that one of the 4 pieces that I want to keep. That one intersection space, if you will, or region, is the solution set for this system of inequalities. Well, today's lesson really brings us to the end of a nice sequence of lessons that we've spent studying systems of equations and inequalities. We've taken a lot of time to discuss how to study these things, the different techniques for studying them. Ultimately, the idea was that we had straight lines that were being drawn in, say, the xy plane, for example, and we wanted to understand how those lines interacted with one another. We were looking for intersection points in the case of systems of 2 equations with 2 unknowns. And in today's lesson, we were looking for systems of inequalities. So we were seeing how regions of the plane interact with one another, but we were still just looking for intersections. And that's the key to basically all of these lessons on solving systems. In our next lesson, I'd like to shift gears quite a bit, in fact, and start talking about a very new topic. We're going to leave linear equations and graphs with straight lines behind, and we're going to move on to things called quadratic polynomials. These look a little like lines and their equations because there will be an mx plus b, if you will, hiding inside. But we're also going to add in a term which will have an x squared. So we'll be looking at things like x squared plus 2x plus 1 rather than just 2x plus 1. That's going to change the graphs tremendously, and it's also going to change the mathematics, the algebra that we get to do with these quadratics. I look forward to talking with you then.